Brief introduction now to the Triton Laboratory TTDMA touch display. First thing we can see is that we have a status of the instrument generally. We have the instrument is currently running in single cantilever mode, temperatures around 25 degrees, frequency is 5 Hz, horizontal orientation of the head. We can also see that the force and the displacement on this with this display here, and we can also tell that we are currently in a run because this red light is flashing, and we can also see that we're running from the stop button on the display. If we were not running, this would be indicating start experiment. The clamp arrangements that are available with the instrument are shown here. Currently we are in single cantilever. It's very easy to change to any of these, and we can show this by pressing over to dual cantilever, going back to the main display, and you can see it's now been entered, and we can actually change the geometry there if we so wish by simply deleting any values that we're not happy with and entering the correct one. And that can be done with all of these things here. Notice as well that we have a modulus range being displayed for that particular geometry. This is very, very useful. It's calculated from the stiffness range of the instrument and is assuming that this is a typical thermoplastic that is being catered for. You can see that you can actually cover quite clearly a range of, say, from 5 to 10 along the bottom here. So it's going from 10 to the 5 to 10 to the 10 in terms of modulus with this particular geometry arrangement. That can be very useful if you're wanting to ensure success of a particular run. You want to make sure that you're going to particularly cover the soft end, and getting the correct geometry can be extremely useful. Next thing along here that we can see is the start-stop button, which we've mentioned already, and the head orientation. The head orientation, this is extremely useful. If you actually change the head orientation, it's being sensed, and this allows the instrument and the software to automatically apply the appropriate corrections. So for example, you may be wanting to run a hair or a fibre of some sort and immerse it into a liquid. The most convenient way of mounting that sample is in the horizontal mode, but the operation to immerse in a liquid obviously entails actually putting that sample vertically into a liquid and to do the experiment. As soon as you do that and press the go button on the system, it will actually apply the appropriate force and keep the hair or fibre in a nice taut manner inside the instrument for testing. So this is an extremely useful automated sample preparation and running capability. Looking at the force and displacement displays, the force is plus or minus 10 newtons, so it's 20 newton range, and the displacement is plus or minus 1 millimeter, so that's a 2 millimeter range. We have defaulted to set them in the middle. It is possible to offset these values if you so wish. This is the most usual and in most cases the most appropriate position for it to be. This can be shown either as a bar display or as a detail display. If we look at the detailed display, we can see that the force that's currently being applied is a dynamic force of around 2.5 newtons with no static force being applied. Below, you can see that the displacement is showing around 30 microns, 0.031 of a millimeter, and that's a static displacement, and a dynamic displacement of 20 microns. The 20 microns is actually the control that we've inputted into the system. So this is actually being controlled at the moment. The reason that we have a static displacement of 31 microns is because the sample isn't perfectly flat and the motor position has been sensed, the displacement has been sensed. If we move now to the status screen, this shows all the very general information. It's got the serial number of the instrument, an interface, configuration, versions, various things that are quite useful to know. It's also showing that there's a chassis fan with a speed going of around 1400 RPM, and there's a head fan which is currently switched off. That can be switched on here, and you'll also notice that there's a key press beep here. At the moment the beep isn't on, but if I press that, you'll notice when I next press a button that a small beep will occur, and it's optional what you do. The reason there's a head fan is that it can be very useful if you're doing a experiment where you want to actually stop a disturbance inside the thermal chamber itself. For example, if you're doing humidity, it's nice to switch that off. It's also quite useful to have it available or not available, depending on if you're going to a high temperature, for example. It's good to keep the inside of the electronics inside the actual head at quite a cool level. And by having the fan on, it just provides that extra ventilation. So for high temperature experiments, that's useful. Low temperature experiments is less important. If we go now to the control button, you can now see that we've got frequency, ramp rate and end temperature being displayed. This is the segment that you're in. So anytime if you've got a multi-segment experiment that you've put into your program, you can actually see the current controlled segment on this display, and it is possible to actually alter these values. So for example here we could actually change that from 5 Hz. We can delete that and put in 10 Hz and enter that value, and that's immediately being activated. Same is true with ramp rate, same is true with end temperature. Finally, if we go to the scope display, you can see that we've got a sine wave being displayed. This is the sine wave that is being outputted from the sample. It's a real display. If you don't believe that, I shall disturb the sample a moment, and you can see that there's a distortion as I have touched that, and that is quite revealing in itself. It shows that it's sensitive to how you actually mount the sample. So in fact it's useful when you're clamping to have this display. If you've got a rubbery sample, it is for the first time possible to actually set a test run up and literally put the clamps on, usually very, very gently. Typically you can do this with your fingers, and clamp a sample at room temperature, a rubbery sample at room temperature. This is normally not the recommendation with DMAs. The normal recommendation is that you cool the sample into the glassy region before you clamp a rubbery material. It is actually possible with this instrument to get around that by actually doing it very, very gently to the point where you snap a nice clean sine wave. So this can be very useful in that respect. Another use of this display is if you've got something like a non-linear behaviour in your material. You get this typically with things like memory metal or with very heavily filled materials, and by seeing the sine wave you can understand the material that you're actually running at that time. The data may look perfectly okay and it may be perfectly reasonable, but you will not have the information without the display of whether it is a linear or non-linear material. So this is again a very important use of this display. That in brief is a good summary of the TTDMA touch display, which interfaces very nicely with the rest of the instrument. Thank you very much.